Bismillah. Hi everybody. Today we are going to discuss least square fitting to data, that is for the best fit curve. By the end of this section, the student should able to find the least square for the straight line or polynomial fit to a set of data points given. Then we perform a group assignment finding the best fit curve to any real data by using MATLAB software. There is a common problem in experimental work to obtain a relationship of mathematical y equals to fx between two variables x and y by fitting a curve to the points in the plane that corresponding to various experimentally determined values of x and y. Let's say we have x1, y1, x2, y2 until xn, yn. To observe the pattern of the points, there are a general form of the curve y equals to fx to be fitted. This curve is called a mathematical model of the data. For example, we have three examples of the model. A straight line where y equals to a plus bx. Okay, for the figure B, this is a quadratic polynomial which y is equal to a plus bx plus cx square. And figure C show that a cubic polynomial y equals to a plus bx plus cx square plus dx, the power of 3. Least square fit of a straight line. So when we have a set of data points, there is generally some measurement error that making it impossible to find a curve of the desired form that passes through all the points. Thus, the idea is to choose the curve by determining its coefficients that best fits of the data. So we have to find coefficient that best fit for the data. Okay, best fit. Okay, this is fitting a straight line to data points. Suppose we want to fit a straight line y equals to a plus bx to the experimentally determined points. That is x1, y1, x2, y2, x3, y3 until xn, yn. Okay, if the data points were collinear, the line would pass through all n points, and the unknown coefficients a and b would satisfy the equations. So let's see equation 1. We have y1 equals to a plus bx1, y2 equals to a plus bx2 until yn a plus bxn. We can write this system in matrix form as, okay, so in matrix form we write as like this because, okay, 1 x1 until xn a b to y equals to y1 y2 until yn is from equation 1. Okay, so this equation we can write as equation 2, mv equals to y, where y equals to, where y equals to y1, y2 until yn, and m equals to 1, x1, x2, xn, and v equals to a, b. This is equation 3. This is same as the equation before. So we can write this one as m v y. Okay, mv equals to y. Okay, so this is mv equals to y. Alright, we also can write the least square minimized error e equals to the distance of y minus mv. If you remember that we have discussed this in best approximation, okay, and we have e square, by we square the error, and we will get e square equals to e1 square plus e2 square plus en square, or this we write as d1 because d is the distance. This is the distance. Okay, the distance 1 square and so on. Okay, if there are measurement errors in the data and the data points will typically not lie on a line, and equation 1 will be not inconsistent. Okay, what is equation 1? Okay, let we see equation 1 just now. So equation 1 will not be inconsistent. Okay, it will be not inconsistent when the data points not lie on a line. Let's say like this. If you have the data like this, let's say we have, this is data xy, okay, and then this is the line. So there is a data that not lie on the line, so this is, we call it not inconsistent with y equals to ax plus b. In this case, we look for a least square approximation to the values of a and b by solving the normal system, that is m the power of t, mv equals to m the power of t y, m transpose, not the power, sorry. This is m transpose mv is equals to m transpose y. If you remember, we have discussed m transpose in the topic of best approximation. Alright, let us assume that x coordinates of the data points are not all the same. So M has linearly independent column vectors, and the normal system has the unique solution. Alright, so where we have V star is equals to A star B star, and M transpose M, okay, inverse M transpose M times M transpose Y. Alright, so if you remember the formula from theorem 6.4.4, the formula, if you remember, x equals to A transpose A inverse A transpose B. Okay, so y equals to a star plus b star x that result from this solution is called the least square line of best fit of the regression line. So from equation 2 and 3, that this line minimize, okay, the distance of y minus mv square is equals to y1 minus, okay, you know that mv is a plus bx1 square plus y2 minus a plus bx2 square plus until yn plus bxn square. Okay, the quantities of d, that is the distance, is equal to y1 minus a plus bx1, the distance of y1, and d2 is the distance of y2 minus a plus bx2, and the distance of dn equals to yn a plus bxn. These are called residuals. Since the residual is the distance between the data point xi, yi and the regression line in figure 6.5.2, we can interpret its value as the error, okay, and yi at the point xi. Alright, if we assume that the value of each xi is exact, then all the errors are in the yi. Then all the errors in the yi, so the regression line can be described as the line. So this is called, this is the regression line. Okay, this is the regression line. Okay, can be described as the line that minimize. This line is the line, okay, the blue color line here is the line that minimize the sum of squares of the data errors. Okay, the data errors. Hence, the name least square line of best fit. So, this is the least square line of the best fit. Okay, where we have the error here. So, this is the error from x1 to the line. So, this is called residual. Alright.